So guys, we go to the next part is length of crease and slug vertical curves based on key factors. The expressions for the minimum length of the crease vertical curves are given in equation 15.3 and 15.5 as follow. So this is the length of crease and slug vertical curves based on the K factor. These are the equation 15.3 and 15.5. So these are the two type. Then next, table 15.5, the value of K for crease vertical curves based on stopping sight distance. So in every design speed miles per hour, there are equivalent stopping sight distance by feet and calculated in this part, and design in this part, but the two is rate of vertical curvature K. Then in this part we have the expression developed earlier. Minimum length of slug curves based on this requirement are also these are the requirement. Then in this part also a table that values of K for slug vertical curves based on stopping sight. So this is the same. So we go next. So in this figure 15.15, a layout of crease vertical curves for design. So all of these are in the book. Then there are the guides for us solve any problem. So we just follow these steps by step. The next, the continuation. So design procedure for crease and slug vertical curves. The design of a crease or slug vertical curves will generally proceed in following manners. So there are 6 manners. First is determine the minimum length of curve to satisfy sight distance requirement and other criteria for slug curves, comfort, appearance, and drainage. Next step, determine from the layout plans the stations and elevations of the point where the grades intersect, BVI. Next, step 3, compute the elevations for the beginning of vertical curves, BVC, and the end of vertical curves, or AVC. Step 4, compute the offset, or Y, in equation 15.12, as the distance between tangent and the curve usually equate distance of 100 feet. When stations are used beginning with the first whole station after the BVC. Then the next step, the step 5, compute elevations of the curve for each stations as elevations of the tangent, positive over negative, offset from the tangent, y. For cruise curve of offset is negative, and for sub curves the offset is positive. So the next step is step 6. Compute the location and elevations of the highest, cruise or lowest sag point of the curve using equation 15.18 and 15.19. So we go to the equations 15.18 and 15.19 in this chapter. So this is the example of design of these vertical curves. So the problem is a cruise vertical curves joining 3% and a negative 4% grid is to be designed for 75 miles per hour if the tangent increase a station 345 plus 60 at elevation of 250 feet. Determining the stations and elevations of the BVC and EVC are the before and also calculate the elevations of intermediate point of the curve at all station. A sketch of the curve is now shown in figure 15.16. So the solutions is for the design speed of 75 miles per hour or T equals 312 from table 15.5. So the maximum length is, so it is goes in this 312 times close open parenthesis 3 minus negative 4 of close parenthesis, so it equals to 2,184 feet. Then the stations of BVC equals to 345 plus 60. Then subtract it by open parenthesis 21 plus 84 divided by 2 close parenthesis equals to 334 plus 68. Then the station of EVC equals to 336 plus 68, 334 plus 68 plus open parenthesis 21 plus 84 close parenthesis equals to 356 plus 52. Then the elevation of BVC is equal to 250 minus open parenthesis 0.03 times 2,184 divided by 2 close parenthesis equals to 217.24 feet. So this is the figure layout of vertical curves, for example for 15.4. so this is the figure of this problem, and this is the table 15.7 elevation computation for example 15.4. so this is the table of this problem. So next is the horizontal alignment. The horizontal alignment consists of straight section of the road known as tangent connected by curves. So simple curves. Figure 15.18 is a layout of a simple Horizontal curves. The curves is segment of circle with a radius, which is discussed in chapter 3 for the case when SSD is an abstract. The relationship was shown to be radius equals to u squared over g times e plus fs, or the coefficient of side friction. So this is the r is minimum radius by feet, the u is design speed miles per hour, then the e is so far elevation feet by feet by feet, and the fs is coefficient of side friction, so g is the gravity. Then next, also a sample example 15.6, dimension of a simple horizontal curve. This is the problem and the solution within, and also the table. Next, horizontal alignment. So the horizontal alignment consists of straight sections of a road known as tangent connected by curves. So it is the same as the first one. Then next, is also the same. Its problem and its solution, and also the table within. So we go next. Compound curves. Compound curves consist of two or more simple curves in succession turning in the same direction, with any two successive curves having a common tangent point. Figure 15.22 shows a typical layout of compound curves consists of two simple curves. So layout of compound curves. Then this is the table 15.10, a table length of circular arc for different compound curves with. Then next example for the 15.7, design of compound curves. Example, its problem and its solutions and table. Just follow and understand. The next reverse curves. Reverse curves usually consist of two simple curves with equal radii turning in opposite directions with a common tangent. They are generally used to change the alignment of a highway. Let's go to figure 15.24, show a reverse curve with parallel tangent. Then the next one is transition curve. Transition curves are placed between tangent and circular curves, or between two adjacent circular curves having substantially differently radii. The use of transition curves provides a vehicle path that gradually increase or decrease the radial force as the vehicle enter or leaves a circular curves. Then the next is the length of spiral curves. If the transition curve is a spiral, the degree of curve between the tangent and the circular curves varies from 0 at the tangent and to the degree of the circular curves dE at the curves and the transitions of place between two circular curves. The degree of curves varies from that of the first circular curves to that of the second circular curve. The next, so this is the length of spiral curves and its equations, the two equation where and its meaning. So we go next. It's table, the continuation. Next is the attainment of software elevation. So it is essential that the change from crown cross section we go back to attainment of supervision. It is essential that the change from crown cross sections to a super elevated one be achieved without causing any discomfort to motorized or cheating unsafe condition. One of the four methods can be used to achieve this change of undivided highways. So in this figure 15.25, the diagrammatic profile showing methods of attaining supervision for a curve to the right. So there are four types. There are four methods that can be used. This is the four. First is crown pavement revolved about center line. Then letter B, the next one, crown pavement revolved around single edge. Then the next, crown pavement revolved around outside edge. Then the last one, the D, letter D, straight cross slope pavement revolved about outside edge. Then we have the fifth, the letter E, the angular break appropriately rounded dotted lines. So that's all. We go next. So next is example 15.8, locations of object near horizontal curve. So we have this problem. Horizontal curves with a radius of 800 feet connects the tangent of two-lane highway that has a post speed limit of 35 miles per hour, while the highway curves is not super elevated. E equals to 0. Determine the horizontal sightline offset HS2 that a large billboard can be placed from a center line of the inside lane of the curve without reducing the required SSD. Perception reaction time is 2.5 seconds and the F is 0.35. Then the solution, we can see the SSD is equal to 1.47 UT plus U squared over 30 times if positive over negative G, then substitute, then determine the M using equation 15.39, then substitute, then get the answer. Then the answer is 9.6 feet. For check solution using figure 15.26, letter B. For R is 800 and V is 35 miles per hour. For figure 15.26B, M is estimated to be 9.5. Then next 15.3, the third part of this topic. Special facilities for heavy vehicles on steep grades. Statistic indicates a continual increase in the annual number of vehicle miles of large truck on the nation highways. Chapter 3 and 9 describe large truck as having different operating characteristics than those of passenger cars, a difference that increases with their weight and size. For example, as the grade of the highway section increase, the presence of truck become more pronounced. Thus, it becomes necessary to consider the provisions of special facilities on highways with steep grades where highway volume of heavy vehicles exist. The most common facilities that address these problems are climbing lane and emergency escape ramps. The next, climbing lanes. A climbing lane is an extra lane in the upgrade directions for use by heavy vehicles. Those speeds are significantly reduced by the grade. A climbing lane eliminates the need for driver of light vehicles to reduce their speed when they encounter a heavy, slow-moving vehicle because of the increasing rate of crashes directly associated with the reduction of speed of highway vehicles on steep sections of two-lane highway and the significant reduce of the capacity of these sections when heavy vehicles are present. The provisions of climbing lanes should be considered. Then, the emergency escape ramp. An emergency escape ramp is provided on the downgrade of the highway for use by a truck that has lost control and cannot slow down. A lane is provided diverse such that when a vehicle enters the escape ramp, its speed is gradually reduced and eventually it stops. So it is important to have emergency escape ramp. So next, the fourth part of this topic, the bicycle facility. So the bicycle, viable alternative mode of transportation. So the bicycle is one of the alternative mode sa biyahe na to. Then it is popular particularly in urban and suburban areas as a means to travel within a community, both for recreation and necessary travels. Thus, the bicycle is an important element in the design of highway. Also, almost all the existing highway and street system can be used for bicycles, but improvement to these facilities are usually required to assure the safety of bicycle riders. So, in this picture, figure 15.27, basic type of emergency escape ramp. So this figure is in the emergency escape ramp, not for bicycle. Next, bicycle lane. A bicycle lane is that part of street or highway usually reserved for the exclusive or preferential use of bicycle riders. Bicycle lane can be delineated by stripping, signing, or pavement marking. This lane should always be in directions of traffic flow. So this figure is for typical bicycle lane cross section. So figure 15.28, typical bicycle lane cross section. So there are three types: curb street by parking, curb street without parking, and street or highway without curbs and gutter. Next, so bicycle path. Bicycle paths are physically separated from automobile traffic and may be used exclusively by cyclists or possible by pedestrians. So this figure 15.29, there are four types. Then 15.30, bicycle path on separate right of way. So